Welcome to the UPC NanoSat Lab Open Doors Day. My name is Adriano Camps and I'm the professor in charge of this academic laboratory. A few years ago, in a university not too far away, since 2007, the UPC NanoSat Lab has developed and launched CubeSats to test and operate Earth observation payloads. CubeCat-2 in 2016, CubeCat-1 in 2018, and FSSCat in 2020 were the first of many satellites to come. In this presentation, the UPC NanoSat Lab students will present the missions they are working on and those that will come in the following years. Welcome aboard, and may the Force be with you. We are located in the Universitat Politècnica de Catalunya, Campus Nord, Building C4 in Barcelona, next to the Unity restaurant in the Plaza de Telecos. In this lab, we develop small satellites and payloads for Earth observation and satellite communications with emphasis in soil moisture, sea salinity and sea ice, and IoT sensors that talk to the satellite payloads. Our facilities include a Class 8 clean room where we have a shaker to simulate the vibrations encountered during the launch and a thermal vacuum chamber to simulate the zero pressure and temperature variations encountered in orbit. We also have a Helmholtz coils cage with an air bearing to simulate the zero-G conditions and the magnetic field of the Earth to test attitude determination and control systems.
NanoSat Lab began activities with CubeCat-1 in March of 2007, which was a multidisciplinary mission that included different payloads from different UPC departments. You can see the orbital injection picture taken from the launcher of CubeCat-1 in the first picture. Our second mission was CubeCat-2. The mission was a project for the European Commission, which included a novel GNSSR payload for L1 and L2 bands called Picaro. It was a very important technology demonstrator because it was one of the first ones using double-band GNSSR for Earth observation. CubeCat-3 was the third mission of the lab, which was left in a mission analysis state due to a lack of funding. It was a project for the Institut Cartogràfic i Geològic de Catalunya that consisted on a microwave payload and a hyperspectral camera. Despite that, the first satellite that was launched was CubeCat-2 on August of 2016, and on November 2018, CubeCat-1 was launched.
One of the current missions is the CubeCat-4, which is a one-unit educational CubeSat mission developed in the UPC NanoSat Lab under the Fly Your Satellite program from ESA Education. On the one hand, a VHF antenna is used to receive AIS packets, while on the other hand, there are two payloads for Earth observation, a GNSS reflectometer and an L-band radiometer. These two payloads use a novel tech demonstrator, an in-orbit deployable antenna, which is one of its main features. Half of the subsystems are commercial off the shelf, like the electric power subsystem, while the others are in-house designed and built, such as the payload and the deployable antenna. Regarding the deployable antenna, shorted as NADS, in this slide there are some examples of the standalone subsystem verification campaign. First, the ambient test campaign is used to verify the subsystem functionalities at normal ambient conditions, such as the antenna deployment as it can be seen in the left side of the slide. Then, the environmental test campaign is used to verify the subsystem, but under extreme conditions. On the one side, rocket vibrations are simulated using a shaker, as it can be seen in the top right part of the slide. Then, temperature and pressure conditions are simulated in the thermal vacuum chamber. A deployment inside the chamber can be seen in the bottom right side of the slide.
CubeCat-5 was a tandem mission of two satellites, the so-called FSS-CAT-A and B, which you can see here. The mission was the overall winner of the Copernicus Masters program and the winner of the Sentinel Small Satellite program. FSS-CAT carried a GNSSR payload for the L1 band and the radiometer, while FSS-CAT-B carried an hyperspectral camera. Both satellites communicated with each other using both RF and optical links. It was the first CubeSat mission providing scientific measurements for the ESA's Copernicus program. They were launched successfully on September 2020. The measurements retrieved provided information about sea ice content, extent, and thickness, and also about soil moisture. Neural networks were used to process all the information, which resulted in many different publications. The results were cross-checked with in situ measurements performed in the Arctic in the Mosaic expedition.
So, the next mission that was conceived after FSS-CAT was RITA, also called CubeCat-6, which started as the winner of the IEEE GRSS Second Student Grant Challenge. The main topic of this challenge was to create a one-unit payload, at most, that would provide useful Earth observation measurements. It is a fact that the world's vegetation is suffering from global warming, mainly due to the droughts affecting the humidity of the terrain. One of the main objectives of RITA is to monitor these changes over time. Even though there are already some satellite missions monitoring soil moisture and ocean salinity using L-band, they are often hindered by radiofrequency interference, which is another one of the topics that RITA would like to address. It will create RFI maps in Earth observation bands to help future missions plan accordingly. Even though in the laboratory we are specialized in microwave payloads, it is a fact that hyperspectral cameras, especially those focusing on the near-infrared bands, are extremely useful for monitoring vegetation state. Thus, this hyperspectral camera that you can see in the pictures can complement the data obtained by the radiometer to obtain even better results. Finally, RITA has two proof-of-concept experiments. One of them is a novel SDR-based LoRa IoT experiment, which aims to recover data from remote sensors, and also to trigger on-demand executions of the other experiments, depending on the recovered data. The other one is a custom-made S-band communication system, to act as the primary scientific downlink for the AlignSat-1 satellite. It has been designed to support up to 2 megabits per second of downlink, allowing us to acquire large amounts of data with the other experiments. As you may imagine, the hyperspectral camera is one of the most delicate instruments in the RITA payload. As cameras are quite new to the lab, we had to perform many tests to make sure that it was working as expected, and also to calibrate the measurements to be able to correlate them with our results. In the middle picture, you can see the hyperspectral camera inside our thermal vacuum, doing a stress test with varying temperature, to see how the different components would react. On the right side, you can see a picture taken from the campus north towards the Tibidabo antenna, which you might be able to see in the image. When calculating the normalized difference vegetation index, you can clearly see a stronger response from the plants, which is useful both for identifying them and assessing their health. With the camera, we not only want to see this, but we also want to detect algal blooms and oil spills on the sea, using different indexes.
The next conceived mission, already in the launch preparation stage, was CubeCat-7, a hosted payload developed also in collaboration with the United Arab Emirates University, focused in GNSSR and ionospheric sounding. On board a 6U CubeSat, it will perform transmission experiments in different bands to test the disturbance of the signal after going through the ionosphere being received with multiple antennas. The CubeCat-8 mission is the latest NanoSat lab development, also based on a 6U platform. The conceptualization began after a call of opportunity for launching in ESA's Aerospace New Spectrum rocket, one of the several small sat launchers close to being operational in Europe. On board of the satellite, various technology demonstrators and scientific payloads will perform a multitude of tasks. A GNSS radio communications experiment will study the propagation of radio transmissions in the ionosphere with a large deployable Fresnel sound plate antenna sporting 2-meter telescopic arms that will be stowed in only 2 CubeSat units. More ionospheric research will be possible thanks to CubeCat-GEA, an IEC payload with an UV visible camera and data compression algorithms. And the Federal Satellite System experiment will test inter-satellite link and resource sharing between the mothership and the POCAT constellations, consisting on several pocket cubes also being developed in the NanoSat lab. The first 2 pocket cubes will be released from an integrated deployer on board CubeCat-8 that was developed as my master's thesis, and it's currently in the testing phase. It has capabilities for up to 3 pocket cube units and adds support for several mounting subsystems. For example, the ADC's actuators such as magnetorquers or reaction wheels, and an X-band transmitter that will allow for high downlink capabilities. In addition, several third-party elements are present in the spacecraft architecture thanks to a collaborative effort, notably an electrospace thruster from GNA Space that will be used for orbital rising, drag compensation, and avoidance maneuvers. And the telemetry module from C3SS will provide GNSS localization and signal for the radio communications experiment, as well as a passive beacon. During the development of the mission, we submitted our concept to Allen Space 3 Award, and elected as winners, the newest OBC was incorporated to the satellite as its main computer, providing, as well as the ADC's controller and communication, the main data handling capabilities. After all the different missions that you've seen, one of the most important facilities of the laboratory, and the one that makes those missions possible in the end, is our ground station. Located in the Observatory of Montsec, developed by NanoSat lab students and managed in collaboration with the EEC, consists on VHF and UHF antennas operating in amateur bands, and an S-band antenna operating in amateur and commercial bands with a newly implemented transmission capability currently under testing.
So aside from the CubeSat mission just presented, we also have other projects such as the Open Pocket Cube Kit, in which we collaborate with IEEE GRSS Society, and also the Pla Estratègic of New Space, in which we collaborate with Generalitat de Catalunya. In this slide, you can see the open positions on different research topics. As you can see, some of them are related to CubeSat or Pocket Cube missions, such as CubeCat-4 RITA, CubeCat-8, or the Pocket Cubes, and others are related to our facilities. In the last slide and also in the chat, you can find the form which you have to fill if you want to contact us, and also more detailed information on the different research topics. Here you have our current members, and as you can see, we range from different types of studies, from bachelor's to master's and even PhDs. So if you want, you can be one of us.
And if after all this that you have seen, you wonder, how did we do it? Here you have 2 quotes. The first one is from Thomas Jefferson. "I'm a great believer in luck, and I have found that the harder I work, the more I have of it." And the second one is from the US Navy Seabees. "The difficult we do immediately, the impossible takes a little bit longer." Thank you for your attention.